Now, you're all looking very flat, very tired, lifeless. Who's hungry? It's a bit early in the lecture to be hungry, isn't it? This is what I love. I love when we do these level 6 courses, evening lectures, 6 p.m. You all look at me like you've got nothing to live for at this point. It's a standard thing. It's hard to explain it. I'll show for people online what it looks like. So if you don't want to be a pixel on a camera, it's a good time to cover your face. That's your heads up. But that's like, less than a pixel. But yeah, see how dead and sad all those pixels look? I know you can't see what you look like up there, but that's OK. That's what you're missing out on, everyone at home. We're having a great time over here, all feeling a bit dejected and bored together. All right, so C++ basics. The first lecture was all about getting settled, talking about the course, getting the environment set up. Today is a blitz of all of the basics of C++. So we're going to go everything from basic types through to some more complicated types. But it's all just kind of like, if you know C, you're kind of going to have a bit of fun, because a lot of things will be kind of familiar but a little bit different, which will be good. And what's the whole purpose of talking about this today? Well, we've got to start somewhere. It's not going to be particularly inspirational. Naturally, the slides are pretty self-evident, so if you read them in your own time, I wouldn't be surprised if you could just figure it all out. But there are like 100 small things here today, because next week we go into some more content around STL containers and stuff, which is important for assignment 1. And we do talk about assignment 1 in the next lecture, which is also tonight. Though for a lot of you to really get stuck into assignment 1, you will kind of need the content from next week. So I think that's really important, because assignment 1, actually I'll talk about that later. It's kind of premature. Let's just talk a little bit about C++ first. And hopefully this room will let us dim the lights a little bit, because it is the evening, and evening lectures are a little bit moody. Okay. Was it? Go a bit further. OK, it said that was further. Is that nice? Nice and... There we go. Don't fall asleep on me, yeah? Having the lights off's a treat. That means you still have to stay awake, but it's a little bit nicer. So basic types. C++ has a bunch of basic types. Now, there's a lot of stuff here. It's all code samples. You can copy and paste these straight from the slides. It's all just HTML. You can literally grab that and paste it somewhere. It doesn't require anything fancy. A huge amount of the content in this slide deck is just main functions, so you could go run it any time. First slide's a little bit obvious, but what do you know? We have the same basic types as C. Ints, chars, doubles, floats. Nothing really new there. We also have voids. You can also do that kind of basic casting like that. Now, when it comes to the C++ compiler, the way that we've set up CMake, and we're going to talk about the assignment later, so I've got this tab open, but I can show you this in the CMake list. It's the same in all of the stuff you have, is you'll see these things here about compiler warnings. WALL, WError, WExtra, pedantic errors, a lot of stuff there. That's going to make your compiler really nitpicky and really aggressive of what it will and won't accept. Because of that, to get some basic code examples working, you will see a few random things like this in the sample sometimes. Because the compiler as it stands, if you just took this code, what it would do without these 3 lines here is it would complain that you've created meaning of life, 6 feet in meters, and letter without using it, right? It's like you created these things and didn't use it. So if you see this stuff, this is like a weird, sad way to use the variable, right? You cast it to void and then you throw it into the ether. And the compiler's like, that'll do for me. That's enough using for my taste. So yeah, I don't even need to run that. Hopefully you all know that it would compile validly. Where things get a little bit more interesting is some extra types. For instance, we have, none of you are interested in the Slido, so I'll just get rid of that for now. Save your necks a bit of pain. We also have some extra types. Notably, we have this thing called string, and we also have this thing called bool. So bools are somewhat self-explanatory type. In C, you're probably used to having ints that you have to hash define something to be a 1 or a 0, right? Feels a little bit icky, doesn't it? The idea of having this int that could be any number, but you're just kind of sort of trying to vaguely, you're asking a question? Yeah. Yeah, exactly. So there's a bunch of stuff like that. Like in C, there's a few of these things you kind of can get in C because of some constructs you build up on top of it. This is baked straight into the language, so you don't need to, it's a good point, stood bool, something like that. You don't need to include anything. It's just part of C++. It can be true or false. That's it. It's written like that. If you do put something else there besides a true or a false, who knows what will happen. That's the cool thing about what we're doing. I said to my tutors the other day, the tutors for this course, one of the hardest things about teaching C++ is that it's this language of endless possibilities. So I've lectured this stuff a bunch before. I've tutored this stuff. And students will always kind of say something to me like, hey, that's basic2.cpp. So if I open up basic2, also, goodness gracious, how do I get rid of this doc thing? Is it the doc? Yeah. OK, thank you. I feel a little bit better now. Geez, that was a bit much. Is anyone else thinking that? It's like giant icons. So I've got this example here. Now, if I want to compile it, I will go. I have a different folder on my computer with the lecture content. So just forgive me as I navigate to it. Cool. Everything today is going to be a 1.2. There are all the files. Now, I can go and make all those files if I want to. But you remember, I can't just write make here. I have to do the same thing we did last time, which is that you can see with the CMake list that this is a CMake run little project. So I go CMake-b build. That'll go and use the CMake list file, hopefully. Got some errors there. Probably need to fix those up. I think the CMake list I have for the lecture code is a little bit behind the course stuff, which is OK. So now I go inside the build folder. And how do I know what to make? Well, the cool thing is if I read the CMake list file, I can actually look at it here. So I can see that the file basic2.cpp is called basic2. So I can simply write make basic2, and that will just compile that one file. If I wrote make, it would go through, and it would compile everything. It's getting grumpy at me for some later examples, probably because we have some errors in them that we have to show you with the lecture slides. So for now, I'm just going to say make build2. That'll build that file, and then I can run build2 like that. Basic2. Sorry, my brain was on cruise control. Make basic2. Basic2. I ran it. Now, there's no output there. Let me just check the camera's still working. The camera has lost the plot. Awkward interlude. Come back. Oh. Sorry, everyone. Just thinking about the people at home. Does anyone here own an Udi? Do you have any? It's like, what's that saying? Getting blood from a rock. That's what it's like with a lot of you. Oh my goodness. That was uncomfortable. That was actually very uncomfortable. All right, so we got our files there. We run basic2. We have a look at basic2. You'll see the true and false. Now, that was a little bit finicky because we had to run our first file, which meant we had to set up the project. But here's a question I get. I was saying to the tutors, you get this question all the time in C++. What if this? What if that? What if we change it to a 1 or a 0? What happens if this is a 1 and this is a 0? Will the code still compile? I'll get these questions from you all term. The answer is always going to be the same thing. Let's go play around with it. We're empowered computer scientists with a computer in front of us a lot of the time. So I can say make basic2, and you know what? It still darn works. Now, as if why does that work? Because C++ is casting the 1. It's doing something we call implicitly casting, where you haven't told it that it needs to cast it, but it's casting it from one type to another, because at some point this would be an int of some sort, and it will get casted through a bool. People say they've lost the screen now, probably because I had my fat fingers. All right, keep going. Very long-winded exercise to explain true and false, isn't it? So we got a true and a false there. Pretty straightforward. We've also got this other thing called standard string. Now, we're going to talk a little bit about what that std : part means in the meantime. But for now, just forget it. Just focus on the string part. So it's just string, like you'd expect. It's similar to a char star. If you remember char stars from C. where a char star is a pointer to a string. In C++, it's not, like, even though you can kind of imagine it's very similar to that in memory, it is different. It's closer to maybe how you'd experience using like a Java string or something like that. It's a nice little abstract object where you can just go dump that in. You don't need to worry about the allocation of memory. It's all sorted. For those of you who are a bit more technical, in C, where some things vary, is that if I just bring up some C here for a sec, if you say something in C like, char, call it word 10, like this, in C that's going to go and create 10 bytes in the stack that you can fill with stuff. If you go and do your char star word equals malloc size of char times 10, is that how you do it? I haven't written C in like 2 years. That'll do. That's close enough. You get the gist. That'll go and put 10 bytes on the heap. And if you go and say char star word equals hello world, that will do neither get stored as a string literal in the code. If you're not familiar with that, you can go Google it. But that's never put on the stack or the heap. That's why you don't actually have to specify the amount, because C just kind of dumps it in. I think it dumps it it doesn't even put it in memory. It just reads it straight from, yeah. The code reads, yeah, exactly. So why I'm pointing this out is because this in some ways can feel a little bit similar to the C-style string literal, right? Because we aren't creating an array here. We aren't, mallocing something. It kind of looks like a string literal. And even, in fact, I'm pretty sure that you don't explicitly need this. You should just be able to do that, and that still works. This is not a string literal, though. Kind of looks like a string literal because it's so similar to that char star one, right? If you just came down here and you said char star course code equals comp 6771, that would also compile. But what this one is actually doing, and we kind of unpack this in future weeks, I'm jumping ahead a little bit here just to kind of paint the nuance of C++, is that this is taking the string literal comp 6771. It is then passing it into the constructor of a string, because this string is the first class or object you've seen in the language so far, right? You're familiar with classes or objects because in Python you have your lists and your dictionaries. In Java you've got your array lists and linked lists and stuff like that. It's a prerequisite to this course, so you understand object-oriented programming. That is passed in as a constructor to course code, which is of type string. A string object is created, which course code references, and comp 6771 is stored inside it. Naturally, it's going to be stored inside it as a byte array, a char array, whatever you will. But that's what's actually going on there. Much easier to work with, though. And naturally, because it's a string, you are also going to have all of the member functions and things, like string size and things. But we unpacked that in a second. It was mostly just to show you that there's some extra types. Don't worry about the std part so far. Any questions? Feeling sleepy yet? No. Has anyone tried the spicy nuggets from McDonald's? I don't know the spicy fries. After the lecture the other day, I went and got spicy nuggets from McDonald's, and I was pleasantly surprised that they were OK. All right, so before we keep talking about it, it's a good time to remind us, like we mentioned on Monday, that C++ runs direct on hardware, unlike Python, JavaScript, etc., right? They either compile things to bytecode, or you got the JVM and complicated things like that. That means that some properties differ. Now, what you're seeing on screen here is stuff that we don't actually really go into a great deal until like week 9. It's not particularly complicated, but how this code actually works is what we go into. But right now, it kind of makes some intuitive sense without trying to understand it too much. This line here looks like it's trying to get the maximum numeric limits of an integer. How exactly that works, a little bit weird. But the max int, min int, max double, min double. So now what I'm going to do is I'm going to, because we've obviously got those files here, system specific, make system specific, run system specific. And you'll see there that I get this printed out. Now, the cool thing about this particular abstraction you see here is that this is different for different computers. Nowadays, a lot of computers I find are pretty much the same. Like 10 years ago, you could kind of be like, oh, Windows 32-bit, Windows 64-bit, something. But now most things are the same. It's probably more interesting if you were to go and run this on like a Raspberry Pi or an Arduino, I imagine. They'd be running some 32-bit systems or with some different sizes. You can also go and look these up if you want to, I imagine. It's like C++ size types, fundamental types. This I don't know if it's here. Yeah, you go. You can see how these things vary here. There's a lot to it. Screen's quite wide, isn't it? So, ints, signed in, unsigned in. So you can see that in some cases, like, a long is like always 64 bits and various other stuff. But my point is this varies in hardware. In the context of this course, you're not going to notice it. You're all working on laptops that are going to be the same as a CSE machine broadly. I think 3 or 4 years ago, CSE did an upgrade where everything's about the same now. But again, it's worth noticing. Obviously, that's where the performance benefits of the language do come from, is the fact that we're direct on hardware. Now, one of the probably most important keywords to note in C++ in this course is the keyword auto. It's probably one of the biggest departures from what you know of in C. It was introduced in C++ 11. Probably one of the most revolutionary things, I think, that happened to C++ to improve the programming. But a keyword that says that the type of the variable on the left-hand side is derived, inferred, by what's on the right-hand side. So C++ figures this out for you. Now, I think where this is, sometimes this can feel like, oh, is this getting into that kind of like JavaScript Python territory, where it's like nothing really has types and it's all just kind of figured out. The nuance to point out here is that what this is this is a keyword for the compiler to automatically determine the type for you at compile time. So once the code is compiled, it is still that type. It's like a compile time help me out. Whereas other languages, loosely typed languages, hello, welcome to the lecture. What were you guys up to? G03. G03? Yeah. Oh. Oh, I actually went to G03. It's pretty awkward. I turned up, the lecture room on Monday. I just walked straight in. I wasn't really thinking. I plonk my laptop down in the middle, and then this person taps me on the shoulder and is like, who are you? What are you doing here? I'm like, I have a lecture. And they're like, no, I have a lecture. And I was like, am I not in here? And he was like, no. And I was like, oh, shit. So I skedaddled over here pretty quickly. But it's very awkward. So I went to G03 briefly. Compile time, autos in compile time. You look at a language like Python and JavaScript, they don't have a notion of types, but they're also really happy to be transient with those types in runtime. You're totally abstracting the type during runtime to the language. So that's a much bigger concept than just auto, which is saying, yep, just figure it out at compile time for me. But extremely useful and something that we use all the time in the course. One of the rules that you'll see in terms of best practices is use auto as much as humanly possible, basically. There's nearly no instances that it's super useful. Maybe if you want that 0 to be a double or something like that, sure. But yep. Const is another really cool feature. Auto and const are we're kind of starting with the cool stuff, but const means what you'd expect. It means that this particular variable cannot be changed once it's declared. You would have seen const. I'm trying to think of languages. There's not really a notion of const in Python. Is there one in Java? Don't think so. JavaScript has const, yeah. I don't remember any in Java. Often we talk about constant variables in C by making them capitals. So we use style. We use style as a way to help denote constant variables, but nothing really stops us changing them. And sure, in C you have hash defines, but as you might know, hash defines aren't actually variables. They're just pre-compiler copy and paste. So they don't give us the same functionality as being able to declare a variable and mark it as const. One thing we talk about a lot in this course is what we call const correctness. Const correctness is a term that denotes, if your code is const correct, it means that everything that should be const is const. Because the way to think about variables is that everything should be const by default, and only when you need to modify it should it not be const. Right? As opposed to just like, I have all these variables here, and oh, that one I really don't want people to touch, so I'll make that const. It's like, no, everything is const unless it needs to be modified at some point, then it's not const. The reason we make more things const, well, people are less likely to accidentally change it. Obviously, it's a signal to the compiler to help people using IDEs and stuff not to change it. This one, I don't have any specific data on it for you, but there are some times when the compiler may be able to make optimizations because it knows something's not going to be changed. We kind of talk about this a little later in the course with a few other things. But if, for example, and this is what we talk about in week 9, if a compiler can actually calculate something sometimes at compile time and it knows it's never going to change, it might actually do the calculation at compile time and just store the constant right there forever. So it has to do less during runtime. So pretty much all benefits, no downsides to using const. You'll also see that there's something that we call east const, which is where we put const after the auto or after the type. So const is always to further to the right-hand side. You'll see a lot of code online that has const auto. I can't remember exactly off the top of my head why we do that. Short answer, and I said I'd be honest with you from the start, is Chris from Google, who's very smart and does all that C++ stuff, says that this is the prevailing pattern generally in industry, according to him. So that's why we put it on the right-hand side. We've got to pick a side anyway for style, so we might as well pick what Chris says as opposed to the other one. Yep. Is const not in C? Was that the question?
Yeah.
Maybe.
It's not used for variables, definitely in some functions, definitions.
Quite possibly. I wouldn't pretend to be a C expert. The full extent of my C work has been in undergraduate studies. So there's probably some kind of random edge cases. And there's definitely cases where you can add a lot with more and more libraries being included too, just like bool. So maybe there's some cases like that as well. Yeah, exactly. So, I'm sure I'll get wrong on a couple of things. And you'll also see here, if you try and modify something that's const, compile time kind of kicks you back. Can you convert const to?
Yeah, const variable to a mutable variable.
So there is, I'm trying to remember. I think there is a way to do that. Const cast. I think a const cast lets you do that. We don't actually teach it in the course because it's kind of considered satanic. Stay away from it because it's usually what are you doing? It's one of those features that's there's ways around this. I can't think of a time you'd ever want to do that. I think it is possible. Naturally, I imagine that what people would probably do instead is nothing stops you creating another mutable variable and setting that to be the value of the const variable, and then that data is copied across and you can modify it. So that would probably be, I imagine, the kind of situation you're thinking about. So definitely a way around that. We already talked about const keyword and where to put that. And we also talked about a few of those things just as we went as well. OK, so I've had 2 questions so far come up. The first one says, why copy initialization is preferred than list initialization? That's a good question. I think you're jumping ahead probably just a week or 2, so I'll probably answer that. Ask that again in a couple weeks when it'll mean more to other people. And then someone asked me about the code. What does void char1, void char2 do? Again, just respecting hundreds of people's times. We did cover that briefly about 15 minutes ago, so you can go grab that in the recording with the first code example. We did talk about that. OK, so in computer science, an expression is a combination of values and functions. Yeah. So there's expressions in C++. And I've started to put test cases here as a way to express this, just to get you comfortable with the catch2 framework, right? Because catch2 is the library that has the test case and the check syntax in it. And you can start to see maybe how we'd write a test here. You can define some variables. It's very similar to the C-style assert. And instead of a function, it's just called test case. So very digestible. Bit of a benign slide. It's mostly showing you that the rules of math also work in C++. Think we can get over that. Same with floating points, like floats and doubles. An important note, I don't, if this does come up in the course, it doesn't come up much. But remember with floating points that there's precision errors. So it's just worth, as a casual reminder to people at the bottom here, that when you compare 2 floating point numbers, particularly say subtracting them, that it's always important to compare them with some kind of diff or delta. And you can see here there's another function here called standard abs, which is the absolute value of something in C++. Now, whenever you see something like this, you can always open it up and paste it in Google and go straight to the CPP reference website. And what they'll often tell you is, up the top, which I think is really important, is how to access it. So you'll see here it says that standard absolute is defined in the header file C standard lib or C math. So you have to hash include C standard lib or C math to be able to use that function. It makes sense because for an efficient language, you don't want to have every single possible function just able to be accessed in scope, right? You should be able to include them all systematically. However, what you will notice, and I guess this is a random point about headers, is that remember when you hash include a library or anything, it itself hash includes other things, right? Because a library, like string or like catch2 might do some math in it at some point. And if it does some math in it at some point, it will need to include C math. So this code example we see here, let me just unmax that. This code example, we're using standard absolute, standard ABS. However, we haven't hash included anything, and that's because the catch2 library itself hash includes something that hash includes something that includes CMath. So in reality, you'll often just try and use these functions, and it'll either work, or you'll be told that you need to hash include something that does it. People might get into like debates about what good style is, like should you always hash include everything so it's needed independently and let the compiler figure it out. Maybe, I think we used to have that some time ago in the course, but I think it's just a little bit finicky. Strings. This one we should definitely be including strings because they're not as fundamental as the standard absolute. So I just got to double check this even works. So let's actually do this one in the editor. Let's open up expression string like this. OK, there's our code. I'm going to go and make expression string. Oh, I think I see why these things are not working. The way I've set up the lecture code, which again I'll share with you all, is that I actually have like everything's kind of done in this main folder. I shouldn't be in that folder. So I've kind of got a build folder here that should be able to just do expression string. Make expression string. See if this works. Yeah. So this is nothing you ever have to do in the course. But again, just a bit of background, because these early weeks are just about adding some background. So all of the lecture code is contained in one repo. I can't remember if I've got that on the course website. I'll just double check if I don't. But I should have it linked somewhere. Sorry? Oh, it's on your computer? Oh, so your computer made a sound, and then you like apologize for being distracting, and then I've like totally destroyed your attempt to not be distracted. It's OK. I love it. OK, so I've got the CMake list file here, and then what I actually do here is I say I'm going to add a subdirectory for all the different lectures, and then all the different lectures, there's another CMake list in it that actually specifically adds all the executables there. So that's kind of how you can, for like really large projects. You'll never work on anything this large in the course, but you can always play around with this if you want. So the reason the compile didn't work was because I went to try and build it from this folder 1.2 here. But the problem with the 1.2 folder is that it doesn't really have anything in it but a bunch of C++. So when I went to hash include catch2 library, it couldn't find it because it's not anywhere. Because if you actually look at the folder structure here, it is all of the lectures, and then the build folder, and then lib in here. So I actually have to go and build and run everything from the bottom. So now I made the expression string. I will run the expression string now. Oopsie. Or it might want me to. Let me check. I think I have to run this 1.2, sorry. Yep. So that's the funny thing about this is that we called make expression string because when you do make expression string, you can imagine what happens is that it goes straight to the CMake. Well, it doesn't do it this way, but conceptualize it this way. It goes to the CMake list file. It looks through all the subdirectories. It expands that out. We see this one here. It sees expression string. It goes, I know what that is. That's where that file is. So it goes and compiles that. And I'll show you this, though. imagine in this folder I run make now, which everything should work. This is just going to blitz through and make every single C++ file in the course for the term, right? So that just built them all. And you'll see if I type ls, all of them are kind of now stored in these folders here. So if I go inside 1.2, you'll see all of this lecture's stuff. So I'll go expression string, and then it runs there. Now, all the tests passed in that particular case. Where is it? Expression string. Cool. You can also see I didn't have to hash include string, but I should here. I think that's probably good style, just in case, you know, but it's not necessary again. But that only is not necessary because catch2 is doing something with string. But otherwise, that would be necessary. And you can see here, if we look at this piece of code here too, actually, I'll unpack that. I'll jump to your question first. Yeah?
Which parts of these are the actual expressions? Like which bits of code, because it's like a section about expressions, which ones are expressions?
Yeah, so
Would it be the ones within like a check and require, like things with booleans, or is it?
yeah, quite often, and it's been a while since I've had to formally define the difference between expressions and statements. But like a statement is made up of expressions typically. This is a kind of programming languages terminology. Like there's a good course called Programming Languages and Compilers. Has anyone done it? Yeah, so it's kind of covered in a course like that. I believe something like this is an expression, and a statement might be more the line. I'll go rain check you on that one. But the reason we call it expressions is just because we're really just talking about what is it? How would you put it? Let me come back to you on a better description of that. I want to get it right. I'm conscious I'm being recorded and I say one wrong thing and then someone quotes me in 2 years and thinks I'm stupid. So good question. Let's look at strings in more detail. This is where things start to get really interesting. So probably one of the more interesting slides we've tackled so far. We've defined some strings. You'll notice the pattern of how we've defined the string here is important. We say auto, and then we say const, and then we define it on this side here. If we didn't have the standard string, and this is actually a great example of const, and where, you know, C++ developers are generally really proficient because it's a complicated language. This will turn expression into a type of standard string, right? However, if I was to drop that and do this, it would turn expression into a char star const, or like const. I can't remember which side that's on. Let's just start with that. It turns it into a char star, like a C-style char star, because in this case, it doesn't have enough information to know that you want it to be a string object. It'll just kind of go to its like base programming, if you will. So that's why we have this standard string here like that, because without it, it won't infer the right thing. And that's what I mean about earlier. We said, you know, what if you want the compiler, you need to give it a push or some guidance as to what auto should be. You can do that. That's kind of what we're doing here. But it always happens on the right-hand side of the equals, right, on the RHS like that. So yeah, define two strings here. We check if they're the same. They're not the same, obviously, so that's going to return true because they're not the same. And then you'll see here that expression has a member function on it called front. And we can also access this with that 0 there. So like, you know, the index 0, the first part of it. This is really kind of where you can feel that string is an object of a class. And also where we can start to see that standard string. On the CPP reference, it's called basic string, and there's a lot of stuff here. But string is a big type. You'll come down here and you'll see member functions. A lot to unpack again. We had some glances at stuff like this. But you'll see it does have a member function called front. Member functions are functions you can call on an object of that class. And here, you can see front there. And what does it do? It tells you lots of stuff here. Returns a reference to the first character in the string. It returns a reference to the first character. It's equivalent to that. The time complexity is constant. So some of the stuff you learn in 2521 or any kind of data structures algorithms starts to come out here. There aren't an exceptional number of like well-documented libraries online for languages where they'll really spec out the time complexity of the operations like that. So it's really helpful to know that it's a constant time operation as well. And you can see that it is actually equal to that because there's other things here like this operator square bracket, which we're going to unpack more in week 4. But it simply says that if you can access a particular element of that string by using the little square brackets you're used to in C. Now, I think the point that I need to get across here is that C generally lacks abstractions when you work with C, right? That's kind of the cool thing about it. That's the fast thing about it. C++ is more powerful usually because it has some abstractions. And in particular here, when you call CXX on index 0, in C, if you do that kind of like square bracket lookup, C will literally only do that on something that's a pointer, and then it will go find that pointer. It will increment it by the number you put between the square brackets, and then it will dereference that value at that point. It's like that's baked into its existence and how it works. With C++, when you do this, you're actually sending a request to a class's, like an object of a class, in this case, string. So string actually kind of gets in between that. Do you know what I mean? And for different objects, maybe it's a string, maybe it's an array, those square brackets, while semantically might mean the same thing, they kind of talk to the specific object because the object kind of abstracts the operation. It's not just baked in for everything all the time, i.e. CXX here is not of type pointer. You know, in C, you can only do that of type pointer. This is of type string in this case. Yeah. Member function, object method, yeah, same thing. Yeah, exactly. Methods, I think we refer to them a lot in 2511, I know specifically, yeah. So a member function is a method for sure. You can see here that if I say auto expression2 equals expression, what it will do is it will create a new type of type string called expression2, which is a copy of expression. I know we cover this in a future slide, so I won't take its thunder, but everything in C++ by default is copied. And that's one of the biggest differences to a language like Java and Python. Whenever you say A equals B in like Java, for instance, it's always like saying I reference the same thing. We call that the language has copy semantics. And again, we get to that in a second. But Booleans, fairly standard. What I'll also point out is that I don't remember which C++ version, might be 14 or 17. They introduced, this is actually a great question for ChatGPT too, because it would find this out way quicker. I don't remember. It was introduced in one of those versions. Instead of the ampersand or the double pipes or whatever, or the exclamation mark for, you know, saying not, you can just use the keywords now, Python-esque, right? So, and I think in a lot of ways this really denotes that, I sound like I'm just kind of being mean to C. It's not really the case. It's just different. It's like C's real benefit is in its sheer stability, you know? And I love that we teach as the first language. I always say C's the best language, I think, to teach first-year computing students because it's the only real popular language I know that you could write down the entire language on a Post-it note if you really thought about it. Everything with C is hard in terms of the execution of it, but the language is so simple. It's so straightforward. C++ isn't, but with that comes more capability. So it's trying to clearly move towards something that is easier to read. Like, why does Python have ands and ors in it as opposed to all those ampersands? Because that's pretty weird when you think about it, right? Like a double ampersand. We should just use the word and. It's kind of understood in the English language, so we have that in C++. Both work. However, if you go read the best practices guide, and this is an example of a bunch of stuff that's in best practices, you will see that we ask you to use the ands and ors for us there. OK, value semantics. I referred to this. When you go and say, hello, is this string, and then you say hello to, these are two totally different variables in different parts of memory, different parts of the, I don't really want to say the stack because maybe it mallocs something under the scene. You get the idea. Different parts of memory. When you compare them, let's see what happens. Let's have some fun with this one. There are a lot of examples to get through today. I think originally I had a plan to do a bit of this on Monday. Make value semantics. We've already made everything. I don't think we need to make any more files. Make 1.2 value semantic. Oop. Oh, thank you. Good spot. All tests passed. OK. So this is also really important because, sure, in C++, when you say hello2 equals hello, it copies it. If hello is 100 megabytes, hello2 will be a new piece of data that is also 100 megabytes. Differs from Java. However, when you compare the two things, it also doesn't really behave like you might expect with C, because if you know in C, whenever you compare two things, it literally compares what it is. Right? So if you have two numbers that are two objects, say, that are the same in C, and you compare them, or two pointers, I guess you should say, that have the same data behind it, they won't be the same. Because in reality, obviously, if you're a computer scientist, you know that hello and hello2 are going to be some kind of reference to memory where the same data is stored in two different spots. However, when you compare it, you get a true. And that's because similar to the dot front and similar to the square brackets, when you compare stuff, and we again unpack this more in week 4, it actually, what C++ does is it says, hello string class, I'm doing this double equals. Can you please check if these two things are the same? You're probably familiar with that from Java, things like dot equals. Postgrads here, do you guys do Java at all before this course? Or is it just Python? Say some words. Fortran. You do Fortran. Java's not required, but you'll do Python. But yeah, OK, cool. Got it. Sweet. We can append stuff to hello2. Nice, high-level language stuff. When we compare it, it's no longer equal, because when you compare two strings, it's going to check the underlying elements. And then we can also do some more member function call stuff on it, too. I don't need to take you through every single little detail. All right, so type conversions. In C++, we can convert types. If you say auto const I equals 0, I is going to be a const int. If you say auto d equals 0, d is going to be a non-const float or double. Can't remember which one it does. Maybe double. Also, another good example, and I can't tell you off the top of my head if the compiler does this, but another great reason to use auto is because the compiler, if it notices you never modify a variable, nothing stops it marking it as const itself if it really wanted to, right? So benefits of auto in general. We checked if d is equal to 0. It is. Then we say d equals I. Now, d is a float. I is an int. Just like C, if you say d equals I, it's going to take I, which is an int. It's going to comfortably cast it to a float, because in general, floats have a higher precision. And that becomes a silent conversion from an int to a double. And then when you check if d is 42 or d is not equal to 41, which frankly, I don't think I wrote this example. I don't fully understand why we're checking if it's 42 or 41. Doesn't really make much sense. You'll kind of get different results. We get that, OK? Casting from C. We can be explicit about casting in C++ through use of something called a static cast. What a static cast does, and you'll see other casts like dynamic casts and const casts, but a static cast takes the value and tries to preserve the value into another type here. So in this case, static cast double I. Why would we want a static cast as opposed to just like a C-style conversion? Yeah, sure. Self-documenting code, that's a great one. That's so much more obvious. I don't know about you, but at a glance at that program, it wasn't obvious to me we were just like randomly casting a variable type there. So the documentation part is good. That's super clear. Prevent overflow? Possibly. I actually don't know. There's a bunch of stuff I could go read up on the docs. I don't know everything about everything. But something like that could be good because it's an abstraction again, right? C++ is about lightweight abstraction. So it's the recurring theme you'll see, because when you cast something like this, there is no abstraction. It's just C doing the casting thing, right? Because how does casting work with C? Well, D is a piece of memory. Then you just say, well, now it's just that. That's like what it is. But the static cast is a nice abstraction. And there was something else on my mind about it's kind of also it's not really necessary with auto on the left-hand side, but we kind of got away with this one because we'd already had an explicit type of D be determined by that auto. So by this point, D was a double, whereas in this case, D actually hasn't been determined yet. So, you know, that will help with the auto part. Yeah. Will this code actually work? I think the test will fail. I don't know why it's here. Some of these examples are from 2019, and I didn't write this lecture originally. Which one is it? Convert explicit. Yeah, it did. Yeah, it doesn't. I don't know why 42 is there. Yep. Yep. The I is an int, yep. Because the compiler would see the 0 and think, I don't need to make that anything other than an int. So it would make it an int. It might even make it like an unsigned int or something. I'm not too sure. That kind of stuff. That kind of stuff is really useful for something that we talk about more in week, I think like 7. Which I won't, like we're kind of, this always happens. So a lot of these lectures are designed to be taught online, but in person you all have so many great questions that we kind of end up taking longer than I think. But there's a great website that we're going to play around with later. There's a bunch of these things around. This one's not really going to be too helpful in this case. I actually thought I think I got something mixed up. But something you can do if you want to understand what's really going on is just paste your code into websites like this. You'll kind of see what it looks like in like x86 in this particular case. I got that mixed up with something else where I was looking to tell me if it was signed or unsigned. Whoops. But still really fun. But yeah, it could be a whole bunch of different types under the hood. If the data type is what? No, it's just like the silent convert. It's just like a C-style cast. I mean, the point of these two slides is to be like there's a C-style way to force the type change, and then there's a C++ way to force a type change, which is to use static cast. You will see another cast out there called dynamic cast. It's a bit more obscure. It tries to preserve the data literally, but just change the type. I haven't really seen an instance where I think that would be useful. We used to have that in, but it just kind of confused students and didn't really serve a purpose. So you can go look that up if you'd like to. All right, just quickly on the questions. Long says PHP is the best language. OK, goody. I like PHP. Why the nested code block? We'll talk about that in week 3. They're asking about what's the point of these bloody braces here. They don't seem to do anything. We'll talk about that in week 3. OK, some other questions from the chat. If the compiler needs information such as standard string to completely determine the type, why even bother using auto? Why not just define the type? That's a good question. So again, I'm going to do my best to answer these kinds of like C++ style philosophy questions. I haven't coded enough C++ in my life to have strong opinions on it, right? Most of this, again, comes from people who would be working with this every day. But the gist of it is that sometimes auto on the left-hand side is good. Sometimes auto on the left-hand side isn't enough to determine the type. You need to add more information to it. So a good idea is that we adopt a convention where we keep the left-hand side extremely consistent. The left-hand side is just for autos, const, the variable name. So when a program is looking at it, the left-hand side's always just that. It doesn't really have type information, and all the type information's on the right-hand side. Because regardless of what's on the left-hand side, as a programmer, you usually need to infer some things from the right-hand side of the equals. So it's nice to just kind of keep that consistent. So a lot of it just kind of comes back to consistency. In the style guide, it says we cannot use classic Boolean operators, but your slides say otherwise. I'm not too sure what that's in reference to. I'll have a quick look. I don't know what you're referring to. Maybe post that one on the forum. There's either a mistake there or like either I've misunderstood something, you've misunderstood something, but we can, yeah.
Could it potentially be like the and or not versus and exclamation mark double pipe? Like the classic C.
Classic Boolean operators. Maybe, but just for time and conjecture, I'll just say we'll follow that up on the forum. Good pick though.
So there's no like the word equals in C++.
Yeah, there's no word equals or anything like that. Yeah, it's just double equals and not equals. Yeah, good question. All right, so functions, C++ has functions, nothing really new there, like C. So let's just move past that completely. One thing that you will see a bit of, though, is function syntax in C++. This is a funny little way that function syntax is evolving. You'll see, classic C thing is return type, and then the function name, and then some input parameters. What you're seeing here is that a kind of more modern way that's starting to become popular is that you always have every function say auto out the front. A little bit like in Python, how it's always like def, def, in front of a function. And you actually put the return type at the end of the function. I believe from talking to people, one reason this is liked a lot is because it kind of reads naturally. Is like you have, OK, here's my function name. It takes in these things, and it returns that. Conceptually, the story is kind of told a bit better. Back when the people that had opinions on this ran the course a bit more, they made that mandatory. I don't care enough about it to make it mandatory, but we talk about it, we give some examples with it. You can do what you want, but we do ask that you be consistent. You'll be knocked down for being not consistent with that, so please be consistent with it. But that is a function syntax that you will see floating around a little bit. OK, functions have default arguments. Again, pretty similar to other languages. Like, I don't need to kind of rehash your entire base programming knowledge, but I think this is kind of similar to JavaScript and Python and stuff. You can have default arguments, default parameters. They always have to be at the end. You can't have default parameters followed by non-default parameters. If you have questions about that, you can just ask as well. And then function overloading also exists in C++. So you can have the same function. You can have a function with the same name, like two function declarations with the same name. And their return types can vary and all this kind of stuff. The only rule is that you can't have two functions with the same name that have the same parameters. Things get a little bit trickier, I think there's some weird exceptions, but again, doesn't really matter. We're just kind of hashing it. Oh yeah, sorry, here they are. Function overloading, find the candidates, select the viable ones. Each argument convertible. I think it's too detailed, but let's try it anyway. Yeah, so it's all compile time stuff. I mean, everything in C++ is compile time stuff. It really doesn't care about return types at all. I think the interesting case, though, here is that if you look, we've got a G function, which is irrelevant, because we've got 3 f overloads. We've got 3 f overloads. The first one's an int, the second one's 2 int, the second one is 2 doubles, but the second double has a default argument. So naturally, in this case, it's going to go to f double double, though more interesting questions could be asked if you were to pass, use 2 ints or something, Does it jump to the, or like 1 int, does it jump to the int? Let's imagine for a second you only had these two here. Horrible highlighting, but you get the point. If you just had one function that took in 2 ints and another function that took in a double and an optional double, and then you called it with just 1 int, it's obviously going to try and go to the double function because it can match that one. And there's obviously going to be rules around this. And the point of this course in general, you'll see this just repeating and repeating, is not that you understand those rules, because I don't know those rules off the top of my head. It's the point that there are those rules, and it hopefully makes you a better programmer in general, because you're able to think about these intricacies. And I think that's, for me, like, if you don't intend to, a bunch of you are doing this course because you're like, I want to be a high-frequency trader and stuff like that, which is like, awesome, go become a millionaire really quickly. But for the rest of people that aren't going to go and do this day to day, the best thing I hope you can get out of the course is that it just makes you think really hard about programming languages, because a language doesn't generally make you think as hard as this darn language does. If statements. Someone asked on the chat, why do we need auto, with the functions here at all? Why can't we just have main? I'm not a language designer, but when you design languages, you're often looking for markers to help you understand what's going on, right? Like in a lot of languages, you have semicolons. Semicolons that help you understand we're done with that statement, time to move on to another statement. So without the auto, I imagine that based on the other language rules, there wouldn't be an easy way for the compiler to tell you're asking to make a function. Again, go to the languages and compilers course if you have. I think it's a cool course. Hands up if you've done it, genuinely. Did you like it?
Yeah.
You can say no.
That was pretty
OK. Great, cool. Jingling, sorry? Yeah, OK, Johannes. So that course and this course were both started by the same professor in CSE. And generally, this was kind of the anyway, long story, doesn't really matter. I just ramble all the time. So if statements, as you'd expect, I keep minimizing and maximizing. Nothing particularly new there. You've got ternary if statements, pretty cool too. Nothing new there. You got switch statements. I can't see why you'd probably use that in this course, but you know they exist, and you can go look them up if you'd like to as well. Now, where things start to get more interesting is this. Sequence collections. So a collection is a grouping of data. A sequence collection means they have order to them. And we're going to talk about the most popular sequenced collection here, which you'll be using a fair bit in the course. Question?
I just noticed something on the previous slide of like something to do with all those fall through. Is that valid syntax or is that just like
It is. It is just in the spirit of trying to not get lost in rabbit holes. I love that you picked that up because I was looking at that and I was like, oh, no one asked a question about that because no, it's like you're right. It's like weird syntax. It is valid syntax. It's not necessary syntax. Yeah, I think it might be the opposite of pass. I don't know. It's a good question. Go Google it as well. Otherwise, we'll come back to it if we have time at the end. So sequence collections. Vector. Vector's a funny phrase. Like I've always found vector funny. Vector in C++ is basically the C++ super array. It's like the array that does everything. It's like a great way to store sequence data, usually better than linked lists, usually better than doubly linked lists, usually better than C-style arrays. It just rules the earth, and it's called vector. Now, obviously, vector kind of makes sense if you think about it, but I wish they just call it array or super array or something, because vector's a little bit off-center for me. But it's a pretty simple structure to use, similar to other high-level languages. In this case here, auto const single digits is equal to standard vector, right? Vector's the data type, like array. We put this little int thing here, just like Java or any other templated language. When you, because again, I guess for postgrads who come from Python, in these strictly typed languages, when you have these, we call them generic types like array and stuff, you actually kind of need to tell it what's inside the array for the compiler to be able to figure it out. So this could be an int, it could be a double, it could also be string, could be bool, could be anything. Any valid type in C++ works. So we create a type with 10 items in it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what we do is we say auto more digits is equal to single digits. C++ has copy semantics, and that means it's going to copy that whole thing. So you imagine each of these here is going to be 32 bits, 4 bytes, right? 32 bytes or 32 bits? My brain. 32 bytes? 4 bytes. Let's imagine it's a. I spend all day doing web development. My brain for bits and bytes is kind of getting mushy. So we got 4-byte numbers there, 10 of them, so 40 bytes stored in that vector. We do that, now we copy it, so now we got 2 lots of 40 bytes. Now naturally, because it's a vector, because it's an object, there's probably going to be some extra data stored in that object, right? Because when you create an object in any language, think of it like a box, object-oriented programming. You got all the underlying data, and then sometimes you might have some metadata. So a really good example for you is let's go and have a look at vector. See if vector works. Vector? STL vector. No. Container vector. Oh, OK. So let's have a look at this. there is a function on vector called size. You do the vector dot size with the brackets. It's a method. It's a member function. And when you do that, it returns the number of elements in the container. So if I did, like in this case, single digits dot size in the brackets, which I do down here for another variable, I get the number. But what you notice, tell me something interesting about the size vector that teaches me about how big the object is in memory. Bit obscure question, yeah. Constant time, right? So great answer. To get the size as constant time. And the fact that it's constant time tells me that the vector has a persistent awareness of how big it is, i.e. when you call it, it doesn't have to go and calculate it every single time. So there's going to be another little, I don't know how big it is, 4 bytes maybe, 4 bytes of memory put aside to actually store the size of it. Maybe there's more, but for argument's sake now, if you've got a vector with 10 ints in it, you've got a 40 bytes plus another 4 bytes, so you've got 44 bytes. So when you copy it, you've got 2 lots of 44 bytes now. It's not just 40. There's also some extra crap that comes along the way. Yep. Yes, yeah. That's what that would be. It's pretty much the same as other OO languages, like private, protected, public. We kind of just talk about objects generally, and then we go deep into classes in week.
So it does feel like this could just be an attribute instead of a method.
Yeah. I mean, there would be an attribute under the hood, but like anything, it's good to have an abstraction of it. Yeah, so it's just an abstraction of that underlying property. Which, again, is useful for compiled languages because the compiler will often just remove that abstraction when it's being compiled. Who's getting hungry yet? Don't eat? No? All right. Vector's pretty straightforward. It behaves like you'd expect with an array. It's got this function called pushback, which is the equivalent to JavaScript's .push, the equivalent to Python's .append. Pushes an element to the end of the array. Dot size gives you 11 because we've added one element. You can also assign something to a particular index, just like you can with a C-style array or a Python-style array, or most arrays really, only for non-const objects. If I tried to make that const, I would get a compile error. Let's use that as a particularly good, quick example. So we got sequence collections here. If I go and run the one I already made before, it works. If I go and change more single digits to const here, what you'll notice is that it now suddenly will not be very happy with compiling. C++ errors are a little better than C errors, but they can still be quite evil. This one here is pretty good. I think Clang errors are pretty good because, again, on Mac, it's using the Clang++ compiler. Error on line 12, cannot assign a return value because function operated that returns a const value. It's OK. I wouldn't say that's a clear error. Obviously, you can probably pick up on what's going on there. What it's essentially saying is that when you do the square brackets with that index, you're kind of making a request to the vector to give you a pointer, a reference, which we'll get to in a sec, a kind of reference pointer to that particular element that you would like to change the value of. And what it's complaining is, hey, you got a return value from it. It returned a const value, and you cannot assign to it. That's what that error is essentially saying there. So that's kind of const played out in action. Let me just, next slide. I was about to say we must be getting to references at some point. So values and references. This is also a massive thing. Hint, hint for assignment 1-2. We can use pointers in C++. You notice the slides so far don't have anything to do with pointers in them at all. We've avoided pointers altogether. That's because you can pretty much totally avoid pointers in C++. That's a good thing. Most problems with coding, as you would know, come from pointer pain. Seg faults, things like that, dereferencing memory, lots of stuff. The reason we don't need pointers is because of a few cool language features, like references, which we're going to talk about, as well as abstractions like vector. So a reference in C++ is an alias for another object. It behaves exactly like pointers, but without the star, really. So if I create an int here, auto I equals 1, that gives me an int called I, which has the value 1. And then I say auto ampersand j equals I. What this is saying here is that I would like j to be a reference. So the ampersand next to a type makes it a reference. So if you say, just randomly here, just writing the code out a bit more literally, int I equals 1. I say int j equals I, that's a copy, right? If I say int k ampersand equals I, k is now a reference. So in a way, how I like to describe it is that when you add the reference to better. Sorry, a few of your brains just like, what the fuck? That was really weird syntax. That is a reference now, which isn't a new concept to you because it really just brings what it's doing down to the level of what you're used to with Python and Java. So this is like Python and Java. When you say what is it in Java? It's like string s equals. I have not written Java in like 7 years. Then it's like string ss equals s. Is that Java okay? Or do you have to go like new? There we go. It's that, isn't it? Great. That's what Java's doing all the time. Java's putting those ampersands there all the time behind the scenes. SS is a reference to S. We don't like to use the word pointer because it is a little bit different, but you can think of it like a pointer, right? Because naturally what's going to happen under the hood is that there's going to be pointers going on, right? Because pointers are just happening whether we like it or not. Every language has pointers. It's just a question of how much they expose to you and they give you control over it. So that's references. Benefits of references. They can't be null. That's one downside of references too, arguably, because j can never be nothing. A reference, like with a pointer can be nothing, has that null state. References can't be nothing. Once they're assigned, they're forever assigned to something and not the absence of something. But the and they also can't be changed what they refer to. This might be a little bit conceptual because I can still, j is a reference to something. So j is forever a reference to that thing, but I can still change the thing it's referencing. So as an example here, back to my really simple code, let's say I have something like this. J will now forever reference I, but I can say j plus equals 1 fine, right? However, obviously, if I was const, I can't ever do that either. So the notion of like a const reference doesn't. Actually, you can have const references. Anyway, it's fine. We'll get to that when we get to it. Just reading the chat. What's funny? Make life easier. Yeah, that's a great point. So now we get into const references too. So a reference to const means you can't modify the object using the references. This is where brains start to get. It's like not crazy hard, but a lot of constant references can get thrown around. What this is saying is auto I equals 1. I is non-const. You can modify I to your heart's content. However, when you say reference, which is a const reference, that way, is equal to I, you can't actually use reference to change I, right? So a const reference kind of puts a lock on the reference. As in, if I copy and paste that code, and I know you can go run this code and stuff, it's pretty fine. What this is saying here is that I++ is OK, but ref++ is not OK, right? And that's because of this const part here, because the reference is const. And it's like funny because you can think, well, wouldn't const reference be that it's always referring to that? And what we're saying is with references, once it refers to I, it's forever referring to I. There's no reason to denote const or not there. It's just ref is always referring to I, and the const helps you determine whether that reference allows you to modify what it's referring to or not. And naturally, too, if you were to just have auto reference there, but you had auto const I, then reference is also not OK there, because your reference is non-const in theory, but what it's referring to is const, therefore you can't change it. I imagine that compiles. I imagine this compiles fine. But if you tried to edit it, the compiler would pick up on it like that as well. Question?
The question about the previous slide about not null.
Null in C++ is the same as C because it inherits all of C. So like,
So it's just like it's 0.
it's reference to memory address 0. Because null exists in C++. Because everything in C is like it's totally backwards compatible with C. We just don't use any of it in C++ because it's nightmare fuel kind of stuff. You know, it's like playing with fire, right? Same kind of thing. You can play with fire safely, play with knives. You go to your kitchen tonight, toss the knife up in the air and catch it. You might be okay. Doesn't mean you should do it, because eventually you'll probably screw something up and give yourself some real pain, right? That's kind of the principle of it. There's an example there you can play through as well. We've got one here, const reference j. This is allowed. Actually, I got it wrong there. See, like the slides, don't listen to me, listen to the slides. It won't even let you make a non-const reference to a const variable, right? So that makes sense. Because what I said was that you might be able to do it, but the compiler would then block you if you tried to actually modify it. But the compiler won't even let you, which clearly makes a lot of sense. Let me just quickly see how much more we have. Can you reference a reference? Yes. But I'm pretty sure what it does is like, if you have like, so imagine my head is a variable, right? If you have I reference my head, and then you have j try and reference I, I'm pretty sure they both just end up referencing my head. Yeah, exactly. Because they're just like, well, I'll just reference the same thing. But again, don't know. That's a great question. Sometimes what I like to do, because like with these build environments, sometimes it can feel a little bit onerous to go and like set up a new file or play around with it. Sometimes when I get asked these kinds of questions, I literally will just go and be like, I'll create a file called like nothing, and then I'll just go do that. And I'll say, yep, int I equals 0, int reference j. I don't need to worry about my style or stuff. That's I, int reference k equals I, or equals j. And then I'll say k++, sure. And then I'll just do like a real quick g++ that. I don't even need an output file because remember GCC and G++ and Clang++ will just compile everything to a.out. And there you go. It compiled and ran fine. So it's like valid. And then naturally I could go further with it. The cool thing about backwards compatibility, I guess, with C to some extent is if you say you're like a new programmer to C++ and you forget the C++ stuff, I'm pretty sure you can always just go and like dump some C in there too. Like we could print them all out, like I, J, K. 1, 1, 1. There you go. I'm still speculating as to how it actually works, but you know the results still good. Sorry? You have to check the actual. Yeah, you'd have to use the big part of your brain. That'd be fun. Functions in C++, everything you pass into a function is passed by value by default. That's copy semantics happening again. So everything in Java is an object, or most things in Python are objects at least. You pass it through a function, it's going to make a reference. C++ is going to copy it. More hints for assignment 1. How do we fix that? Well, we pass by reference. Passing by reference is where we simply go and add an ampersand to things like that, so that now when we call it, like this case here, it actually just passes in a reference to it. And that, I guess there's a couple things here. One is that sometimes that can make programming a little bit easier. Because naturally with the default, like with C, with the default behavior of passing by value, right? You'd know this from kind of early C programming. You can't actually write a swap function to swap two variables. You have to go and do the whole, first year computing pointery poo stuff up here. I have the right one, right? Yeah. Can't really see anything from down here. We have to, use pointers. You know what happens with pointers? We probably like pointers are scary. You know why it's scary? This little thing here that I just highlighted. That's where it all goes south, right? Dereferencing a memory address. Scary stuff. So we can do that, but what's better? References. We can nearly write the code more intuitively, like the other higher level languages, where we simply pass in a reference of something through X and through Y, and we create a temporary variable, and we swap them around. So obviously, there's a little bit of inefficiency there, naturally, right? Like, because pointers are going to be the more efficient. Are they? No, same thing. There's still a temporary thing. Ignore what I was about to say. So references, super handy, super convenient. You can't accidentally dereference null, which is great. Really intuitive too. You don't have to get into the whole passing addresses of stuff through functions. And the other main benefit is they have all the niceness of standard semantics with the efficiency gain of not having to copy variables. Hint, hint, assignment 1 again, because you imagine things can get pretty big. You have a vector of like 1,000 items, and you pass it into a function. Even if you're not swapping it, it doesn't have to be a swap function, just pass it into a function. It's like, bam, and then you put that in a loop. Now you loop it another 1,000 times. You're talking about moving like 1,000,000 bytes of memory through the little sad computer at that stage. Question?
Would that code be equivalent to creating within main, like I prime and j prime as references to I and j and passing those into swap? Would you need to like change the function signature of swap for that to work, or is intent?
For this example?
Yeah, like if you were to pass references into the functions of the parameters rather than the actual variables themselves. Or is that?
Oh, that's a good question. I like that question. Not to imply I don't like your other questions, but I think I understand what you're saying. I think, and tell me if I'm wrong here, but it's like, what if we just have that, and then we were to go and create like a reference there and a reference m.
Yeah, I was going to suggest like my question was like not changing int x int y from intent x intent y, but like yeah, that what in main that's what I was saying to do. Yeah.
Oh, so you were just saying this too.
Yeah, like if that
Same thing.
or if you would have to do what you just did and get rid of and in the
No, like I mean, getting rid of that would just break it. But this is fine too, because like you got to think of references as like you know, if you pass in k and m there, all it's going to do, all the compiler does with that is just they just go and replace it with I and j.
right.
Like it doesn't actually go and change your code or anything, but.
So like basically, if you have the intent in the function prototype, it'll like create a reference, like in, like.
Yes. Yeah, this is the key part. Yeah. Yeah, for sure. Cool.
If I pass on k and m, would it not just pass on the address?
Not really, because let's imagine we have this for a second. What ends up happening here is k and m are references, but because they just get they're just references to I and j. So at the end of the day, there's still a thing that is kind of passed in. So I and j are the stuff, and that's what gets tried to be passed in, but it's kind of the function that determines what it gets. So if the function itself isn't asking for a reference of it, then it just gets the thing itself. Yep.
So if you were to get rid of those, would it just break, or would it do the same thing where it doesn't actually swap as like the original example?
Yeah, it just wouldn't swap it. It'd be like, yeah, the original example. The worst kind of error, as we'll talk about in a sec. OK, comparing pass by reference and pass by value. There you go. If we're using, OK, so auto by value, const string reference, vector of strings. OK, so the first one, we're passing in a string to a function, and it's copying it. Takes 153 nanoseconds. If used by reference, it goes down to 8. Now, I don't know exactly how big the string is, but naturally, right, a reference is going to be, how big's a reference? Maybe. Yeah, it depends on the memory address. So it could be 4 bytes. Nowadays, like this MacBook and your laptop's probably 8 bytes because we're all running 64-bit operating systems, right? But same gist. It's the size of a pointer. So a reference is going to be 8 bytes. So naturally, you know, if a string has many characters in it, it's going to be more. And in this case, you can see that like a vector of strings is like, what, 2,000? And just a reference to it's like 13 nanoseconds there too. So we're talking about, you know, naturally a proportional time saving to the size of the item itself. some other questions here. Yeah, some questions about why do we write things a certain way. Most of the answers to that's just going to be style. Nothing else on the Slido. I'll bring the Slido up for a second, because I know there's a bunch here that just sometimes don't write it down and you don't have a question. OK, declarations versus definitions. Also, I know we're not really having a break tonight. What's the point of having a break and you're getting home 10 minutes later, right? We'll just keep going. Just get it done. I'll just talk louder till we're all excited. Declarations and definitions are just up here now. Interesting keywords. A declaration is, what's a good definition of it here? A declaration is essentially when we make the type and name known to a compiler. Function prototypes are a great example of declarations. Most things in a .h file are declarations. A definition is where we actually kind of give it the body or the value, right? So for functions, a function declaration is just the return type and the parameters and the name. But a function definition is where we give it the function body that tells it how it operates. With a variable, a variable declaration is the type and the name, and a variable definition is where we give it the value too. Often when we write code, and that code's quite small, so I'll pull up it here. Yeah, often when we write code, we'll do these things together. So here, for instance, that's a definition. We have define and declare. Definitions are declarations as well. So that's a declaration, because and also definitions generally allocate memory when it comes to variables. So this one, there's no memory allocated. In this one here, there is memory allocated. We have given it a value. This here is also a definition, because we've created an empty object. And these things here aren't really anything. They're just void operations that don't matter. This is a function definition, because we've given it a body. This up here is a class, which we'll get to kind of in future weeks. But you kind of know classes a little bit for now. Both of these are declarations, but this would be a class definition. Why does this matter? It's a great question, right? Does anyone want to tell me their thoughts on why it might matter? Definition versus declaration. Yep.
Well, they make things like functions where you can just have it. You only need to have the declaration to use the function. You just have the definition somewhere else that you can do. Your file says the definition is some other thing.
Yeah. I mean, that's the difference between them for sure. Like declarations also have the benefit of being, you can have them multiple times. You'll notice this, because in most languages we go and write function prototypes, but a lot of the time you can write a prototype as many times as you want, I think, in C++, and it'll be okay. What I've come to again like about C++ is because it's such a complicated language and such a nuanced language, it forces you to be exacting with your spoken language or your written language, right? With the English part of it. And it's not something we assess in this course, but it's something I'd encourage you all to embrace, because genuinely, what C++ taught me how to talk about programming better with people. Because again, it's so nuanced, I had to understand the nuance. And because you understand the nuance, it's easier to just literally speak to people about it, because they know exactly what you're talking about. People throw words around all the time, like, oh, that's the whatever. But if, for instance, you're talking to someone who's also educated on this topic like you, and it's not really unique to C++. These things exist in other languages. It's just C++ kind of begs it out of you. Can you go look at the declaration? Can we declare that? Can we define that? Being able to distinguish those two things, I think, is super valuable. Pretty random fact, though. Looping. No real questions. That's OK. So loops. For loops, like while loops are what you'd expect. For loops, though, we do have these for range statements, which you'll see in a lot of powerful languages like Python and JavaScript. They follow a very similar type of pattern where it's like you say for, and then you give it a type, and then you give it the variable name that's going to be used for each loop. And then on the other side of the colon, you give it the list you're iterating through. This is for vectors in this case. Slightly different syntax, but all kind of the same. the main thing I'd point out is when it comes to for loops, you'll generally be looping over a range. It's a little bit like, who here has done JavaScript before? Be at least 50% of you. Right? It's the undergrads plus the postgrads that have done 60/80. When you do a for range loop, it's nearly always const. Because most for range loops, you're kind of reading values. And if you're doing something with them, it's usually into a new space. Similarly, with C++, most for range loops are const references. Because if they're not references, it also means every time you copy something, it's going to be quite slow. Hint, hint also for assignment 1, that you imagine you've got like a standard vector of standard strings here, a whole bunch of stuff. If you and let's just call that, vec for fun. If you say, well, for auto const v inside of vec, I'm going to do stuff, every single loop you have is going to be, again, copying all those bytes. And if you wrap that loop inside another loop, then you've got a square problem on your hands now, right? The reason I keep making that hint is because assignment 1 does have performance elements in it, but truthfully, probably 50% of the battle of performance in assignment 1 can be solved just by using references everywhere. Well, not literally everywhere, like everywhere they should be, Which again, similar to const, it's kind of like everything should probably be a reference unless it doesn't need to be a reference.
So in that case,
Yeah, exactly. Yeah. So like in this case here, we're not mutating anything in this function. We're trying to find all computer scientists in this kind of abstract function. So because we don't need to even modify it, even if we're calling this function once, we just make it const because we don't need to get a copy of it,
Is it right to say that the only reason that you use the reference in there is for memory purposes, to speed it up, or to not have to copy each time?
Yeah, it's mostly performance, for sure. I mean, what I'd say is like references by default is just all about performance. But then when they can be advantageous beyond that is things like swap. They become a better use than pointers. So by default, it's performance. But the other side is that they help us avoid pointers. For statements, very similar. Don't need to baby you on that one. Yep.
I noticed this before with my religion, but most of the things with like I plus plus or I minus minus have been the other way around in a lot of the examples I've seen. Actually, so plus plus I and minus minus n.
Minus minus I or plus plus I is usually marginally more performant if the compiler doesn't figure that out for you. But we'll loop back to that in week 4, if that's all right too. It's a good question. There's enumerations in C++. You don't really need these in the course, so it's kind of included here for completeness. They're often just kind of better than like a list of hash defines. You know what it's like with hash defines. You like hash define 5 different things, and you'll give them a random number like 1, 2, 3, 4, 5. So another good example of how there's an improvement on C by being clearer with semantic there too, because that code's kind of better to understand. All right, so here's the thing. Just jumping in a few random orders here. File input and output. There isn't really much file input and output in the course either. So I'm not going to talk to this slide extensively, but you will see it in some of your assignments, and we will kind of touch on it more in future weeks. But basically, when it comes to file writing, one thing C++ does very well is that it actually treats files the same way it treats standard out. Because in C++, standard out is talking about you streaming information to a buffer. So standard C out in C++ is a stream where you just kind of send stuff to. Similarly here, if I create a file, in this case I'm creating an output file stream. That's what this is. I'm kind of glossing over the underlying details here. This is saying create a variable called fout for file data.out, and its type is an output file stream. And then what we do is we open a file called data.in, and we're essentially going to use a for loop where we keep reading in data from data.in, and every time we read in data.in, we're going to print out a number to the terminal, because cout is standard out, and then we're going to also send that number to, well, yeah, whatever we read into the file out. So this is a good example of us sending I to both a file and to standard output. And all of those different things, file inputs, file outputs, standard in, standard out, they're all dealt with through the same kind of syntax. I think there's a tute question on it or two, but as you'd imagine, reading from standard in is just the same thing as standard out, but with the operations swapped around as well. This is a for loop. Oh, here. You mean this part in particular, right? Or it's a good question. I'm assuming that like this here is going to, like I'm pretty sure what this is basically doing is it's trying to open the file, right? Because when you create a standard input file stream, when you create an input file stream from this, it's going to try and open the file data.in. And it's going to load that stream like, what do they call it? Like, I remember from OS, I've forgotten now. The file IDs, right? Like all the information about that file, like the access to the stream is going to be stored in the in variable. And if the file can't be opened, that's going to become null or some other kind of undefined amount. And this here always returns true because it's a successful assignment, and this here then gets evaluated after it. So the if is basically evaluating on that in there as to whether it like worked or not. It's very obscure. Again, yeah, exactly. Yeah, exactly. You could probably like, I mean, it's really just this. I don't know why the person who wrote that example wrote it so obscurely like that. Yeah. But again, there's a few other things we could unpack on that. I'm not expecting you to just be like, oh, that's straight away. Go play with it, but that's the gist of it. Yeah.
What is the truth value of in run arrow I? Because that's in like the place where usually that's like a condition of x.
Yeah, so a similar kind of thing here. This doesn't need any kind of I++ because this is the thing that happens every loop. It's the condition. And when you try and read in from the file into a variable, it will always be truthy unless there's nothing to read in which it's falsy. So whilst it's always like true, true, true as it's consuming stuff, and then when it runs out, it's like falsy at that point.
That expression has a truth or a false value, but then it has like the side effect of also affecting the value.
Yeah, because it will end the loop because it's the condition of the loop. Now again, I want to point out with this one that when it comes to this input file stream stuff, like I don't know this off the top of my head. I would be Googling a few examples and stuff like that. The purpose of this is not so you're like, oh, I'll go write one off the top of my head. It's just that's kind of what it looks like. Input files, output files, it's very similar to standard C in and C out. Now, can't decide. So one quick tidbit also is hash maps. Hash maps are the equivalent of Python dictionaries. We talk about this stuff a lot more next week. So week 2 is mostly about vectors and other types of containers, other types of hashes and things like this. So I don't actually need to spend a lot of time with it now because we will go through this example next week. But it is just like a Python dictionary, or in the case of JavaScript, it's like a JavaScript object. In the case of Java, I don't even remember. What's it called in Java? Hash map. Oh, yeah, it is. It is. So it's a pretty straightforward key value pair associative container. You have one data type references a second. It's more powerful than a lot of the scripting language maps because like in Python and to some extent JavaScript, all the keys have to be strings, right? Like strings have to map to any kind of value, whereas here you can have any kind of value mapped to any other kind of value. Now again, a lot of code to unpack here, but it's very similar to vector. It's an object, it has methods, it has members. You can go and create it like this. It just happens that instead of standard vector of one data type, it's an unordered map of one data type to another data type, and you can kind of store it in like that. Again, could spend 10 minutes on this example, but we talk about it in week 2, which I think is an important note because Again, I'll talk about that with assignment 1. It's all good. Program errors, not going to spend a lot of time on this. Again, this is all just about communicating. There are 4 types of errors. There are errors that happen when you compile code. Code can't compile, it's a compile error. There are errors that happen when you try and link code. For most of you, this is a compile error in your head, but in reality, the code actually compiled successfully. The compiler just couldn't link files together. The classic case of that is if you create a program like this. This code actually will have compiled successfully, but what the program kind of does, like this file compiles, but it expected that another file compiled over here with the isc CS6771 function, and it tries to link them together and it can't find it. If you're not too sure what that is, that's OK. But many of you have kind of thought about linking from maybe another course. But if you're not sure, lump that into compile errors too. We have runtime errors, which is when like a file can't be opened or someone divides by 0 or something like that. That's your program compiles, runs, and crashes. And then we have logic errors, which is when your program compiles, runs, doesn't crash, and is still wrong. And the mentality that we always want you to get in is that these errors are the best because they're transparent and you figure out what's going on, right? So compile errors are a good thing. If it's not a compile error, it's a runtime error. If it's not a runtime error, it's a logic error. And the further you go into that, the less likely it is that you find it, the more likely it is that your code had an impact on someone. And that's the cool thing about these really strict languages like C++. They're heavy on the compile errors. Sometimes they're really hard to even just get to compile because it's such a tight, strict language. And that's a good thing. You should embrace that. Many of you probably do because things like TypeScript and stuff are super popular. Anyway, don't pack up because we've got 10 more minutes. But that's the end of that part of the lecture where we cover the basics of C++. We will go more into vectors and unordered maps next week.